Hello everyone. In this video, we'll be discussing my solutions to the AP Physics C Mechanics 2012 Practice Exam FRQs as released by the College Board. As a disclaimer, I do not own any of the questions below. They are the property of the College Board, which does not endorse this product. I will be discussing my own solutions to each of the problems. However, I will also be pointing out the points awarded by the College Board in their official release for each of the questions. Let's begin. To start, consider the following experiment. A block of mass 0.3 kilograms is placed on a frictionless table and is attached to one end of a horizontal spring of spring constant K, as shown in the figure above. The other end of the spring is attached to a fixed wall. The block is set into oscillatory motion by stretching the spring and releasing the block from rest at time t is equal to 0. A motion detector is used to record the position of the block as it oscillates. The resulting graph of velocity v versus time t is shown below. The positive direction for all quantities is to the right. For part A, we wish to determine the equation for v of t, including all numerical values for all constants. Well, looking at this plot, we see that it is a trigonometric function of some kind, and it begins from its middle value at t is equal to 0. It then has a period from the first blue point to the second, which is 0.7 seconds. So we know that t, the period, is equal to 0.7 seconds. Next, we note the amplitude. Here, the amplitude is the largest value attained by this plot. And according to this plot, we see that the amplitude is approximately A is equal to 0.16 meters per second, as this is a plot of velocity. Then, we note that the sine of x is equal to 0 at x is equal to 0. So, as that also holds for this plot, we see that this is a sine function. However, a sine function looks like the following orange plot. It begins by increasing in value. So it is the negative image of this black plot. So all we do is we take the amplitude and we multiply it by -1. So the amplitude is negative 0.16 meters per second. So the total velocity v of t is given by the amplitude times the sine of omega t. But we note that omega is the angular frequency and is given by 2 pi times the frequency. And the frequency is 1 over the period. So this is equal to 2 pi over the period t. For us, we see that the period is 0.7 seconds. So omega is equal to 2 pi divided by 0.7 seconds. And this is equal to 8.98. For ease of calculation, we'll call this 9.0. And of course, this is measured in radians per second. Then, proceeding, we see that the velocity v of t is equal to negative 0.16 times the sine of the angular frequency, which here is 9.0 radians per second times time. So this is the plot of velocity as a function of time. As a note, you can get 1 point for writing the final answer, as given here, without showing any work. However, You could alternatively start out by writing that v of t should have a form which goes as v of t is equal to negative v max times sine omega t. Then you must use that omega is equal to 2 pi over t to get another point. And upon solving for omega using that t is equal to 0.7 seconds, for which you get another point, you get the final answer. Note, however, that you can also get full credit for this problem just by writing the final answer as given here. Next, given that the equilibrium position is at x is equal to 0, we wish to determine the equation for x of t, including numerical values for all constants. Well, to start, we note that the integration from 0 to t of v of t dt should give you the position at x of t. Then, doing this integral out, where we note that we use t primes in the integrand so as not to confuse it with the t in the integral bounds, we get that this integral should be equal to negative 0.16 times the integral from 0 to t of sine 9.0 t prime dt prime. Well, the integral of sine is negative cosine. And remember, because we have this 9.0 inside of the sine, when you take the integral, you have to divide by this omega. So this integral becomes, well, on the left we get x of t minus x of 0. And solving for this improper integral, let's say, we should get that this is, well, it's negative cosine, so the negative out front vanishes. So we have 0.16 divided by 9.0, where we divide by this omega because of u substitution. So this should be 0.16 divided by 9.0 times cosine of 9.0 t plus some integration constant. Next, assuming that x of 0 and the c constant cancel each other out, we get that x of t is equal to 0.16 divided by 9.0 times cosine of 9.0 t, which is the equation for x of t. As a note, you can get the final answer without showing any work, as you could in Part A. Alternatively, you can get 1 point for showing that cosine is the integral of sine, and you get 1 point for the correct x max value, which here is equal to 0.16 divided by 9.0. And again, you get that from doing the integral of sine. Moving on, we next wish to calculate the spring constant, K, for this spring. Well, noting that x of t is equal to 0.16 divided by 9.0 times the cosine of 2 pi over 0.7 times t. I suppose here we're now calling 2 pi over 0.7 9.0. This implies that a of t, which is equal to the second derivative of time, of position with respect to time. This is equal to negative 0.16 times 9.0 times 9.0 times cosine of 9.0 t. Then, using Newton's second law for a spring system, we find that F is equal to ma of t, which should be equal to negative k x of t. This implies that negative m times 0.16 times 9.0 times the cosine of 9.0 t, this should be equal to negative k times x, which is 0.16 over 9.0 times the cosine of 9.0 t. So, canceling like terms on either side, we can get rid of the cosine on either side of the equality. We can get rid of 0.16 on either side of the equality. Then, we find that, solving for k, that k is equal to m times 9.0 squared. So this is equal to 0.3 kilograms times 81, which here is equal to 24.3. And we'll call this about 24 newtons per meter, which is the K constant for this spring. Next, consider a different experiment. The block and spring arrangement, as above, is now placed on a rough surface, as shown below. The block is displaced so that the spring is compressed a distance d and released from rest. On the dots below, we wish to draw and label the forces, not the components, that act on the block when the spring is compressed at a distance x is equal to d over 2, and the block is moving in the direction indicated below each dot. On the left dot, we wish to draw the forces acting on the block when it is moving toward the equilibrium position from a compressed distance of d over 2. Well, to start, we note that acting on this block is the gravitational force, F of g, which here is always equal to mg, and to counteract this force is the normal force, Fn, which again is equal to mg. Here, when the block is moving towards equilibrium, we see that the spring is pushing it towards equilibrium. However, because it's moving to the right and it is on a rough surface, friction is pointing to the left to counteract this motion. So, pointing to the left is the friction force, which I'll call FFR. And this is equal to mu times F of n, where mu is the coefficient of friction of the floor and the block. And pointing to the right, we find that the spring constant is what causes the block to move towards equilibrium. So this force, FSP, is equal to KD over 2. So the spring constant is directly related to the spring force. Alternatively, suppose the block is moving away from the equilibrium position. So now it's moving to the left. This occurs when the force acting on the block This occurs when the block has already moved past the equilibrium position. Then, once it's moved past the equilibrium position, we have the spring force moving it to the right. It's accelerating it to the right. However, the velocity is moving to the left. So we have another force which counteracts this motion to the left. This would be the friction force. So here we have two forces acting to the right, both the friction force and the spring force. So first drawing again the gravitational force Fg, which is equal to mg, and the normal force which counteracts this, Fn, which is equal to mg. We find two forces acting to the right. Firstly, we find the spring force, Fsp, which is equal to kd over 2. Similarly, we find another force acting to the right, which is Fr, the friction force, which is equal to mu times F of n. So these are the two force diagrams acting on the block when it's moving at different points in time. As a note, this problem gets 1 point when we write the correct normal force and gravitational force. For the left diagram here, the student gets 2 points for having the correct horizontal forces. That is, the spring force moving to the right and the friction force moving to the left. And for the right diagram, we get 1 point for having the horizontal forces in the same direction and for having the correct values. As a note, a student can be deducted up to 1 point if the vectors in the right diagram, which point horizontally, so these two vectors, if they do not touch the dot, the student can lose at most 1 point. Also, the length of the individual vectors is not considered in scoring this problem. Finally, consider the following question. We wish to draw a sketch of v versus t in the case where we have a rough surface, assuming that there is a negligible change in the period and that the positive direction is still to the right. To start, we begin this system with the block compressed, so its first velocity will be to the right, or positive, and it will be increasing until it passes through the equilibrium position. So, this plot, because there is friction, should decrease in amplitude as time increases. And noting the correct places where the plot should intersect with y is equal to 0, we find that the following plot suffices for visualizing this new v of t function. We have a plot whose amplitude goes up and through each of the listed points. However, the amplitude decreases as time increases. This is because as time increases, we're losing more energy to the environment by way of the friction of the rough surface. So the student here gets 1 point for having a 0 of the plot at this particular location. A student also gets a point for having damped oscillations. That is, the amplitude of the plot decreases as time increases. And the student gets 1 point for starting at t is equal to 0 here with the velocity increasing in the positive direction, as we have here. Next, let's consider the second problem. You are to perform an experiment investigating the conservation of mechanical energy involving a transformation from initial gravitational potential energy to translational kinetic energy. In Part A, you are given the equipment listed below, all the supports required to hold the equipment, and a lab table. On the list below, indicate each piece of equipment you would use by checking the line next to each item. Well, As a note, my solution may differ from yours. However, there are some general grading guidelines which I will point out. Below is my own solution. However, that does not mean that it is the only solution to this problem. To start, I will be using a track, a cart, a meter stick, and a stopwatch. The only grading criteria for Part A is that the meter stick and the stopwatch were both selected, regardless of what else is picked. Next, in Part B, we wish to outline a procedure for performing the experiment. Include a diagram for your experimental setup. Label the equipment in your diagram. Also, include a description of the measurement you would make and a symbol for each measurement. In lieu of time, I won't be writing out the entire description of the experimental procedure. However, I will speak it. My diagram is below. To start, we use the track to lay out the following. Then we place a cart at some height h at the top of the track. This height h is measured by the meter stick. We then let the cart travel down the ramp to point A. Then, at point A, we begin a stopwatch, as indicated here, which gives us a time t it takes for the cart to travel from point A to point B on the track. Point A to point B is an entirely flat portion of the track with zero friction. The distance between A and B, d, is given by the meter stick measurement that we perform before this experiment begins. Then we take this time it takes to travel from A to B and the distance along which it travels to find the velocity at the bottom of the ramp A. So here, the velocity v is equal to d over t. This velocity v is used in calculating the kinetic energy. Ke is equal to 1/2 mv squared at point A. That is at the bottom of the hill. At the top of the hill, we use h in order to calculate the gravitational potential energy, Ug, which is equal to mgh. Then, let's proceed to the next part of the problem. That is, we wish to give a detailed account of the calculations of gravitational potential energy and translational kinetic energy both before and after the transformation, in terms of the quantities measured in Part B. Well, let m of the cart, the mass of the cart, be unknown, as we have not specified it and we have no way to measure it. So we let m be the mass. Then, initially, we have the following. At the top of the hill, we have that the kinetic energy is equal to 0 because the cart is not moving. And we have gravitational potential energy, Ug, initially at the top of the hill, is its maximum value. That is, it's equal to mgh, where h is the height of the hill. Then, at point A, we have the following. We have that the final gravitational potential energy is equal to 0 because the cart is 0 meters above the ground. However, we have a kinetic energy, Kef, which is equal to 1/2 mv squared. However, because of how we calculated v above, we find that this should be equal to 1/2 m times d squared over t squared. Then, to show that we do not have to know m, we note that what we want to find is that Ug0 is equal to Kef. If this equation holds, then the conservation of energy holds. So on the left we have mgh, and on the right we have 1/2 m d squared over t squared. As we can easily see, the m's cancel on both sides. So m is not an important quantity, the mass of the cart, in this problem. As a note, for grading, a student would get 1 point for clearly calculating KE0, 1 point for calculating UG0, 1 point for calculating UGF, and 1 point for calculating KEF. And the student gets 2 points for correctly writing the instantaneous velocity v. Here, we've already noted that v is equal to d over t. Next, assume that after your first trial, your calculations show that the energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. Again, in lieu of time, I will not be writing the solution out. Instead, I will be speaking some reasonable explanation for this result. Well, we found that KE is greater than U. So we've measured that V is too large. The velocity V is too large because otherwise this equality would hold, but it doesn't. So either H is too small or V is too large. This can occur in two ways. Either one, the meter stick wasn't exactly accurate. However, this doesn't make a ton of sense because if it measured that H were too small, it would also measure that D were too small because D was also measured with the meter stick. However, another reason for this to have occurred is that the stopwatch could have been started too late or ended too early. If this were the case, T would be too small, meaning that V would be larger than normal. Another example of how this could have been caused is by unintentionally pushing the cart down the ramp. So a push could have been an example of what happened. As a note for grading here, a student gets 1 point for a reasonable cause for the energy increase and 1 point for a reasonable explanation for this cause. For part E, on all the other trials, your calculations show that the energy decreased during the experiment. Assuming you made no mathematical errors, give a reasonable physical explanation for the fact that the average energy you determined decreased. Include references to conservative and non-conservative forces as appropriate. Well, the average energy could have decreased from friction. So there could have been friction forces acting on the cart or air resistance. However, more likely it would be friction forces. This force is non-conservative. A conservative force, as you recall, is a force that can be written as negative du dx for some function u. We end up calling this function the potential energy of the system. More importantly, though, conservative forces do not preserve energy conservation. So, although gravity is a conservative force here, and so perfectly converts the potential energy at the top of the ramp to kinetic energy at the bottom, the friction force on the track converts some of this energy into heat. This energy escapes into the environment and so cannot be added back into the system. so there seems to be a net loss of energy at the bottom of the ramp. As a note for grading, students get 1 point for a reasonable cause for decrease related to non-conservative forces, as for example the frictional force. Students also get 1 point for a reasonable explanation related to this cause. That is, the ramp is too rough. Moving on to the third and final question of this exam, consider the following. A ring of mass m, radius r, and rotational inertia m times r squared is initially sliding on a frictionless surface at constant velocity v0 to the right, as shown above. At time t is equal to 0, it encounters a surface with coefficient of friction mu and begins sliding and rotating. After traveling a distance L, the ring begins rolling without sliding. We wish to express all of the answers below in terms of m, r, v0, mu, and fundamental constants, as appropriate. Part A. Starting from Newton's second law in either translational or rotational form, as appropriate, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. For 1, the quantity we wish to find a differential equation for is the linear velocity v of the ring as a function of time. To start, we use Newton's second law. That is, F is equal to m times a of t. Then, the only force acting on the ring as it's both sliding and rotating is the friction force, which is mu n. And here, because this force is slowing down the ring, this should be a negative force. So it's equal to negative mu times m times g. Therefore, as a of t is equal to the time derivative of velocity, we find that dv dt is equal to negative mu g. So this is the differential equation in question. Next, we wish to find a differential equation determining the angular velocity omega of the ring as a function of time. Well, the rotational analog of Newton's second law is the torque equation. That is, tau, the torque, is equal to I, the moment of inertia, times alpha of t, the rotational acceleration. Here, I is equal to mr squared times alpha t. And this should be equal to the rotational analog of the friction force, which here is just mu mg, the friction force, times the radius from the center of the ring, which is r. So, as alpha of t is equal to d omega dt, we find that d omega dt is equal to mu g over r. As a note for 1 and 2, for 1, students get 1 point for using F is equal to ma, which is equal to the negative of the friction force. Students also get 1 point for knowing what the friction force is, the exact form as given here. And students get 1 point for noting this equation. For part 2, students get 1 point for noting the following equalities. They get 1 point for knowing the rotational analog of a force, that is just multiplying it by the radius in question. And the student should get 1 point for knowing that this equality holds. Next, we wish to derive an expression for the magnitude of the following as the ring is sliding and rotating. Firstly, the linear velocity v of the ring is a function of time. That is, we wish to solve the following differential equation. dv dt is equal to minus mu g. Well, we note that integrating both sides of this differential equation, we get an integral from 0 to t of dv, and this should be equal to negative the integral from 0 to t of mu g dt prime. And this easily is seen to be equal to minus mu g t. Then, as the left-hand side is equal to v of t minus v of 0, we get that v of t is equal to v of 0 minus mu g t. And this is the velocity as a function of time. As a note, a student gets 1 point for setting up this integral, and they get 1 point for the correct answer. Next, we wish to find an expression for the magnitude of the angular velocity omega of the ring as a function of time. Well, the differential equation in question is d omega dt, which is equal to mu g over r. Then, integrating both sides, we get the integral from 0 to t of d omega is equal to the integral from 0 to t of mu g over r dt prime, which is equal to mu gt over r. Then, the left-hand side of the integral becomes omega of t minus omega of 0. However, omega 0 vanishes, as there is no rotation at t is equal to 0. So, omega t should be equal to mu gt over r. That is, omega t is equal to mu gt over r. And this is the answer to these two questions. As a note, as above, the student gets 1 point for setting up this integral and 1 point for getting the correct answer. Next, we wish to derive an expression for the time it takes for the ring to travel the distance L. Well, after a distance of L, the velocity v, the linear velocity v, should be equal to r omega. As a note, this occurs at the distance L because after L, there's no more sliding. So, the only linear velocity is from the rotation of the ring. So, what we find is that v of t is equal to r omega. And this is equal to v naught minus mu g t. Then, noting what we found for omega above, we find that the right-hand side is equal to r times mu gt over r. Then, adding mu gt on the right over to the left, we find that v naught is equal to 2 mu gt. And finally, we find that t is equal to v naught over 2 mu g. So, this is the solution in question. Students here get 1 point for noting that the linear speed when slipping stops is equal to r omega. The student also receives 1 point for the correct answer. Next, we wish to derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. Well, immediately after it's traveled the distance L, the time that we found above applies. So, plugging in this time to v of t, we find that it's equal to v naught minus mu gt, and using their shampoo, we get that v naught minus mu g times v naught over 2 mu g is equal to v naught over 2. So, this is the correct answer for the velocity as a function of time. As a note, students get 1 point for substituting the above time into this correct kinematics equation. So the student could get part C wrong and still get part D correct because all D is graded on is using the T from part C. Finally, we wish to derive an expression for the distance L. Well, we know that the velocity is given up until the time t. So L should be the integral from 0 to t of v of t dt. This should be the distance, L, in question. Then, plugging in for v of t, we get that this is the integral from 0 to t of v naught minus mu g t prime dt prime. And these should also be primes, just so that there's no confusion with the upper bound on these integrals. Then, performing this integral, we find that this is equal to v naught t minus 1/2 mu g t squared, evaluated from 0 to v naught divided by 2 mu g. Then, plugging in for the bounds, we find that L is equal to v naught squared over 2 mu g minus 1/2 mu g v naught squared over 4 mu squared g squared. And simplifying this slightly, we find that we get an answer of 3v naught squared over 8 mu g. And again, this is equal to L. So we've derived an expression for the distance L. As a note, students get 1 point for setting up the following integrals. They get 1 point for the correct answer given here. And this concludes my rendition of the FRQ solutions to the AP Physics C Mechanics 2012 practice exam. Thank you.